Advanced Math, Lesson 42, Conic Sections, Circles, Constants, and Exponential Functions. Conic sections. Okay, so conic sections covers the graphs of 4 different shapes. And a conic section is pretty much what we see here. So a conic is 2 cones pretty much held end to end. 3-dimensionally, it's like if you were to take a string and attach it at a single point in space, you could stretch the string out this way and then twirl it, in a circle to make the cone. And then you could take that same string, stretch it out in the opposite direction, twirl it in a circle, and make that cone. Or you can think of it as 2 strings emanating from a single point being twirled to make 2 cones. And that's a conic section. So 2 cones pretty much touching end to end like this is the conic shape. And then the section is if we take a Cartesian coordinate system and we cut this conic at any point within its shape. So if we were to just take a plane and horizontally slide it through one of the cones, we get the graph of a perfect circle. Now if we take the cone and we slide it through one of the cones at an angle, we get the graph of an ellipse. All right, so, okay. Now next, if we slide the coordinate plane at an angle that's parallel to the slant of one of the cones, so we slide in the graph parallel to this cone, we get a parabola, and then we slide that parallel graph up and down along the cone to increase the size of the parabola. We can make it really narrow by sliding it really close to this section, or we make it really wide by sliding it far away. But the key is it's parallel to this slant, because a parabola will never touch this second half of the conic. Now the last one is the hyperbola, which is different from the parabola because a hyperbola does touch both sections of the conic. It runs perpendicular through them, and you could slide it closer to the center, farther away from the center, but it intersects both conics and is seen as it's seen as like a parabola and its mirror image. And so that's the graph of a hyperbola. So that's our introduction to conic sections. Those are the 4 main conic sections that we're dealing with in this book. And today we're going to do an overview of circles and the general form of a circle. Again, the definition of a circle, which I'm pretty sure we've talked about, is the locus of all the points that are equidistant from a single point called the center. This single point is the important part on the graph of a circle, or the function, or not the function, but the expression or representation of the circle. So if we were to pick a single point in a coordinate plane, go a radius away from it, and then make a perfect circle, we're going to pretend that's perfect. This single point is represented by the coordinates h, k. Now the center will always be h, k. And you may have noticed we've done some function work in the book so far with the letters h and k. And those function works are likely the graphs of circles or ellipses, maybe even parabolas or hyperbolas. But h and k are some common numbers that we use in the graphs of conic sections. So the coordinates h and k will always be the center of the circle. When we graph the center of a circle, the general form of the equation is going to be written like this. The radius squared, that's r, is going to equal x minus h squared plus parentheses y minus k squared. And that's the general form of the equation. Or sorry, not general, that's the standard form of the equation, and that's how we'll usually identify it. So sometimes they'll give you, once we start learning other conic sections, we have to be able to pick out this equation of a circle. Let me apply this. So let's say this circle has a radius of 5? Yeah, 5. Okay, let's say the circle has a radius of 5, and the center coordinates are at, we'll say 4, and that looks kind of like 5 or 6. 5, we'll say 6. It's a little bit bigger. So we'll say that this coordinate is 4, 6. So h is equal to 4, k is equal to 6. And again, we have one initial relationship that we see right here, which is that h is the x-axis, k is the y-axis. And we see that reflected in the equation because we have x minus h, y minus k. Now, some of you may recognize that this equation is very, very similar to the distance between 2 points equation. And that's because it is. The way we think of it is that one point would be the center of the circle, another point would be the end of the radius or a point on the circle. So if we did distance of 2 points, that would give us the radius squared, right? So the distance between the point of the center of the circle and a point on the circle is distance squared. And we represent that just like this. So to plug these values into this equation, the way this equation would look is r squared would be 5, 5 squared being 25. So when we plug 5 into r squared, we get 25. That's going to equal x minus h, so x minus 4. Again, another trend here, we see the opposite values, plus y minus k, k being 6, so y minus 6 squared. And that's how we would graph this equation right here. This equation of this circle. So we can see this information. If we take this number, we find the square root of it, we have the length of the radius. If we take the opposite of 4 and the opposite of 6, so positive of negative 4 and negative 6, so we take the opposites, positive 4, positive 6, that gives us the center of our circle, and then the square root of this number gives us the center, the length of our radius. So using that logic, we're going to backwards graph this circle. So this x plus 3 squared plus y minus 3 squared equals 16. Well, I just wrote that off camera. So this is the equation of a circle, and we're going to graph it. So with the knowledge that we just learned, our h and our k are the center of our circle, so we take the opposites. So h comma k is going to actually equal negative 3 comma positive 3, because remember we switched the signs. So if we go to negative 3 positive 3, that's the center of our circle. So negative 3, 3. And then to find our radius, we just take the square root of this number. So that's 16. The square root's going to be 4. So we go out 4 in every direction, draw our circle. That's the graph of our circle. Now, some of you may be asking, what if our radius wasn't a perfect square? What if our radius was 18? Okay, well then for the length of the radius, I would just put square root of 18. And it's that simple. Or since square root of 18 can be simplified, that could also equal 3 root 2 if you were to factor it. So I could put square root of 3 times the square root of 2. So that's acceptable for your radius. That's it for circles. So we do have to memorize this equation form and then be able to decipher that information to graph circles, or take the graph of a circle and put it into this form. Now we're going to talk about constants in exponential functions. So the exponential function, the base function, is f of x equals x squared. The graph thereof looks like this, passes through the point 0, 1, and then it just rises up exponentially into infinity. Now the constant in an exponential function is going to be this point right here. All your exponential functions will pass through the point 0, 1, except of course if we have 1 to the power of x. That's not really an exponential function because it doesn't matter what number you put in here, you're always going to get the number 1. So this one does not count, but any other exponential function where the base number is not 1, like x squared or f of x equals 2 to the power of x, these exponential functions, they're always going to pass through this point 0, 1. And the reason why is because any number, doesn't matter, any number to the power of 0 equals 1, except for 0. Sorry, we can't have 0 to the power of 0. That's not 1. It's a little bit different. We'll talk about that later. Or maybe we won't. That's actually kind of like pre-calculus, calculus stuff. Maybe we get into indeterminates. I'm ranting now. So anyways, the constant in our exponential functions is the point 0, 1. Now, how this plays out in graphing functions is it gives you a point that you can start at, but difficulty is sometimes our exponential functions go in the opposite direction. Sometimes they're wide, sometimes they're narrow. So to figure this out, again, just use your 5-point minimum to graph the function. And then another thing that will help you is rewriting the function as soon as you get it. So one of the examples they give us is y equals 3 to the exponent of negative x. That's going to be a difficult substitution. I could rewrite this equation before I start substituting. That'll save me a lot of time. So if I think of this as 3 to the power of negative 1 times x, I can take 3 to the power of negative 1, and I can rewrite that to be 1 over 3, right? And then I just take this number to the power of x. So instead of having to do all this crazy substitution, I can just find the equation of this function, which is the exact same as this, same number rewritten. So I could rewrite it. That makes it a little bit simpler. I know that if I take 1/3 squared, the higher the exponent gets, the smaller the number is going to get, because the denominator is just going to get bigger and bigger and bigger, and the numerator will always be 1. So this function is actually going to go to the left. And you'll notice that any fractional base number that has 1 as the numerator is going to be oriented this way. It's going to be going to the left. And the reason why is because that number 1 and that denominator, the higher the denominator gets, the smaller and closer to 0 it's going to get. So any fractional exponent or fractional based exponents are going to go in the opposite direction. Let's see here. A tougher example. Let's say they tell you to graph the function y equals 1/2 negative x minus 2. The way I can rewrite this is this negative 2 value. I can actually resplit it into a multiplication problem. So this first half, I'll take it as 1/2 to the exponent of negative x, and then the other one I'll take as the exponent of 1/2 to the negative 2. This simplifies to just become 2 squared. 2 squared is 4. So this whole right side simplifies to become 4. So now I have 4 times 1/2 to the negative exponent of x. If I, again, rewrite this as 1/2 to the exponent of negative 1 times the exponent of positive x, that flips that again. So this just becomes 2 to the exponent of x times 4. And then if I multiply these, I just end up getting, can I do it as 8? Hold on, let me think here. Oh, no, I think I'll just leave it like that. So yeah, I'll leave the exponent like that, so that way I'm not doing high exponents. I can just do small exponents and then multiply by 4. If I really wanted to, I could write it. Or no, I couldn't write it because of PEMDAS. So yeah, hey, I was right. So this is as simple as we can make it. But again, rewriting your exponential equations will make graphing much easier. So this is not my final answer, but this is what I'll use to find my final answer. So I'll plug in my 5 points, and then I'll graph it, and I'll know that it's going to have the point 0, 1. I just got to figure out if it's going to the left or to the right. Since this one is not a fraction, it looks like it'll be going up and to the right. If I were to plug in 1, 1 times 2 to the power of 1 is 2 times 4 would give me 8. So at 1, it would be all the way up here at 8. So this one's going to be a very, very steep function. That's it for this video, and I'll see you guys in class.